Hey guys, I wanted to record this set of notes because it is very long, because we're going to have to do two notes in one. So the first thing I wanted to talk about was some adjustments that were made to the due dates for things. So you should see on the Schoology course page an updated calendar, and then at the top an updated announcements and reminders with new due dates for the long-term assignments. So the Unit 6 notes book and the Unit 6 test review and vocabulary have new due dates. They've been pushed out a little bit. You can check for those dates. So if you turn that in early and we're done with it, awesome, I graded it. It's in the grade book. If you were unsure what to do, then no problem. We are going to have an extended due date. And I believe for you guys, that means that the notes book is due Monday, March 1st. And then the review / vocab is due the 4th, I believe. So there's some more time. We've also adjusted the test date. So we're definitely going to make accommodations for that. As far as assignments that were due during the winter storm, there are quite a few missing assignments. You'll see that they're missing in home access. In Schoology, you would see them as a grade of 0 because I can't put missing in there. You can definitely still turn those in for full credit. I'm not going to take off anything for anything that was due during the winter storm. However, you still need to take care of it, okay? So I'm going to be doing progress reports just kind of based on where we are right now, but it doesn't mean like you can't turn those in. And again, like this, I think it was the speed, velocity, and acceleration assignment. If you have it, turn it in. I'll give you full credit for it, all right? Okay, so I need you to open up your notes books. We're going to finish the whole thing out. I'm going to do the best I can to keep it quick and to not take more time than needed, but at the same time, kind of got to do it, all right? We lost a lot of red days, so I'm trying to just do the best we can to get us back to where we need to be. Okay, so the first thing we're going to do is talk about changes in motion. So that should be roughly, that's the third set of notes in your notes book. So the process of changing place or position is what motion is. And usually we can tell when something has changed its place or position by using a reference point, right? So a stationary point used to determine the position of an object. And those can be any object, really. It could be, a street corner. Sometimes we give directions like the intersection of this street and that street. It could be a landmark, like a place. We can say it's, third house to the left. So we understand there's a reference point, right? So a reference point is needed to determine whether an object is in motion or not. So some examples would be parked cars, trees, buildings, landforms. Every time I go to any store, I'm always kind of making those reference point, notes in my mind of like where I park my car. I know I'm, next to the outside door, or I'm closest to the street, or third lane in the middle, things like that. Those are reference points. You can pause this video at any time to have time to type in the words as needed, okay? All right, I'm gonna keep going because you can always pause. So the first thing we're gonna do is talk about distance versus time graphs. We also refer to a distance versus time graph as a speed graph, because if you think about it, 15 miles per hour, that's telling me how far I went in a certain amount, how fast I went in a certain amount of time. It gives me that sort of time, that distance again. Like I went 15 miles, there's my distance. In an hour, there's my time. So distance is plotted on the x-axis, time is plotted, distance is plotted on the y-axis, time is plotted on the x-axis. I'm trying to do this fast for you guys. Time is plotted on the x-axis. That is the only constant we're gonna see. We're gonna look at 3 different types of graphs today. Distance versus time, speed versus time, and position over time. The y-axis will change a little bit. The x-axis is always time, because that's what we're looking for. As time goes by, what is happening to the motion of an object? So the steeper the slope of the line on the graph, the faster the object is moving. So I can see that the green line represents an object that has covered more distance in a shorter amount of time. It's faster. So when we look at, and I'm going to go ahead and just put all of these up so we can kind of talk through them real quick. When we look at a distance versus time graph, we have to be able to interpret what the lines mean based on what they look like to us. So it would tell us the motion of that object. So constant speed is going to look like a straight line slanted upwards, like this, because that tells me that the object stayed the same speed as time was going by. The distance changed, and as time was going by, it was maintaining a constant speed. Acceleration, so that would be a change to speed or direction. In this case, I'm seeing the speed increasing is going to be a curved line, right? No motion, meaning as time was going by, the distance stayed the same. So they weren't moving. They're an object at rest. It's going to be a flat horizontal line. The line will never slant downward because total distance cannot be subtracted. So in other words, this type of graph, distance over time, just shows us motion in general. It doesn't really give us the idea if it's a forward motion or a backwards motion. It's just showing us that the object is moving. Speed versus time graphs. We also call this an acceleration graph because remember, speed versus time would mean that this is really distance over time, because that's what speed is, distance divided by time, plotted over another timeline. So acceleration changes to speed or direction. Particularly, we're looking at speed here. The steeper the slope of the line, the faster the object is accelerating. So in the other graph, that green line meant that the object was going faster, but it also meant that it was moving at constant speed. In this case, it means that it's actually just getting faster. So as time goes by, the object is increasing its speed. So again, let me click through all of these so we can see them as we talk about them. So in a speed versus time graph, so I can see speed is on my y-axis, time is on my x. Constant speed now looks like a flat horizontal line because that tells me that the speed is not changing as time is going by. That's constant. Acceleration is going to be that straight line up or down because that's going to tell me that as time is going by, it's increasing in speed or decreasing in speed. So now we can see a downward slope. No motion is going to be a flat horizontal line, but it has to be at zero because think about it. That means you have zero speed as time goes by. That's the third diagram at the bottom. The line will slope upward when speeding up, and the line will slope downward when speeding down. So faster, slower. Then we have our third graph, which is a position over time graph. This is very similar in meaning to distance over time. It's just now we can see what direction the object's going. Is it going away from a place of origin or back to? So in other words, does it have forward or backwards motion? So position is on the y-axis, and again, time is always on the x. And here's where we talk about a word called displacement. Displacement is a difference in position between the starting point and the final point. So in this graph, the displacement represented on this graph is zero because the object started and ended up at the same point. It went away from home and then it went back home. So very much like a distance time graph, constant speed is going to be a straight line up or down. So in that first picture, the object went away from home at a constant speed and it went back home at a constant speed. Acceleration is a curved line up or down because it's either getting faster as it goes away from home, or it's getting slower, or it's getting faster as it returns home, or slower as it returns home. The line and no motion is going to be a flat horizontal line because, again, the position of the object does not change as time goes by. The line will slope upward when an object is moving away, and it will slope downward when it's moving back towards the starting point, away from home, back home. So here's some check-in questions, okay? We're just going to do them together. So the first question is, write a short scenario to describe the motion represented on the graph. So let's use the example of Ms. Castro makes a trip to Target. So this is a position over time graph. So what I'm looking at is sort of the distance and time it took me, but also the direction I was moving away from home, back home, right? So Ms. Castro took 2 hours to get to Target because it was far away, because it was the only one open, because they're all closed because they don't have any food because of the winter storm, right? So it took me 2 hours to get to Target because I had to drive really slow because ice everywhere. And I was moving at a constant speed because I was keeping it at 20 miles per hour the whole time because it was really dangerous. Then once I got to target, I spent 2 hours there because the lines were really long. Then it took me 2 hours to come back home. So now if you see, I'm here at this point, still moving at a constant speed. But then I realized that I forgot something. It was really important. It was eggs. We all need eggs. And that target didn't have any, so I had to go faster to a target that was much farther away, 80 miles away, in those 2 hours. So I can see my story matches my graph. Okay, second question. It says rank the runners from fastest to slowest. Well, if I'm just looking straight, I know the steeper the line, the faster the person. So that's David. David is the fastest. And then Eddie, and then Adrian. However, we got a cheater here because look at Eddie. Eddie doesn't even start at the starting line, and he still don't win. So cheaters never prosper. But the speed from fastest to slowest would be David, Eddie, and Adrian. But remember, Eddie's a cheater. Question 3, describe the differences between a distance time graph and a position time graph. There's one main difference. Position over time will show me the direction the object is moving, away from home or back towards home. Is Castro going to target or going back home? Question 4, how is it possible to have a distance of 100 meters but a displacement of 0 meters? Because you went someplace and then you went right back. So displacement means that you ended up where you started. Which segment of the graph represents constant speed? Now let's pay attention. This is a speed over time graph. So these lines don't mean the same as a distance over time or a position over time, right? So we want to know when it was constant, and that would be section D right here. Because in section A, I'm getting faster, I'm getting slower, I'm getting faster, and now I'm maintaining the same speed as those 5 seconds go by. Section D would be constant speed in a speed over time graph. Okay, let's take a 1-minute break here. Pause if you need to. We are going to move right into Newton's laws of motion because we have to. Both of these notes, though, really were not the longest notes in the world, okay? So we can do this. So let's take a breath, take a pause, get a sip of water, and then we'll be ready to go. Okay, so we're gonna move on to our last and our 4th set of notes in our notes book. That's it, we should be done after that. We're gonna learn about Newton's laws of motion. For this one, I will play video, so hopefully you can hear the sound, and if you can't, then they're embedded in the slideshow that you have access to anyway. But let's see if you can, I'm not sure. So the first question is, who is Isaac Newton? Who is this guy? So Isaac Newton was primarily a mathematician. However, because he understood and could explain concepts, very abstract, difficult concepts, in very concrete and provable ways, because of that strong math mind he ended up becoming one of the world's greatest known scientists because he applied all of that mathematical understanding and knowledge to be able to explain why things happen in the natural world. So Neil deGrasse Tyson is a physicist and kind of like a science celebrity. And he's going to talk a little bit about Isaac Newton.
I mean, just look at his writings. The hair stands up on the head here and there, but if I did, it would stand up on the back of my neck. Your voice is one of the man is connected to the universe in ways that I've never seen another human being connected. He's got a super connection. He discovers the music, figures out that white light is composed of colors. That's kind of freaking out. Taking colors in the mirror, put them back together like white matter. think that's the analysis of the news. How's that work? Red voters are like green over against white. The laws of optics discovers the laws of motion and the universal law of gravitation. And Frederick says, where are these orbits of the planets? Why are they in the shape of overlaps? Flat, circle, whatever. There's some other things, some other planet. I get back to it. So it goes here, comes back, a couple months later, there's one. Actually, cutting sections of the planet, which you cut. And I said, find this out, how do you determine this? Well, I had to invent integral difference in outcomes to determine this. Then he turned 26. Then he turned 26. We got people slogging from calculus in college just to learn what it is that I was invented. Right. So that's my
Okay. So, Isaac Newton, how we're going to relate to that information is we're going to focus on his 3 laws of motion. We've really kind of talked about gravity already, which is a big, law of gravitation was a big discovery. Kind of explains why everything does what it does within anywhere where 2 objects with mass interact with each other, right? So now we're just going to watch a short video about the 3 laws of motion, and then we'll go through an explanation to fill out your notes. So if you are kind of fast forwarding through this, again, all these videos should be embedded in your student slideshow. And if they're not, then I'll give them to you at a later date. Hopefully you're able to hear them though.
Have you ever noticed that it's harder to start pedaling your bicycle than it is to ride at constant speed? No wonder what causes your bicycle to move. Or thought about when it goes forward instead of backwards or sideways. Here's not anyone did. It wasn't until the 17th century that Isaac Newton described the fundamental laws of motion and understood the answer to those 3 questions. What Newton recognized was that things tend to keep on doing without our ready to. So when your bicycle is stopped, it stays stopped. And when it's stopped, it stays bound. Objects in motion tend to stay in motion. Objects at rest tend to stay at rest. That's Newton's first law. Physicists call it the law of inertia, which is a fancy way of saying that moving objects don't spontaneously spin slowly or change direction. And as this inertia that you must overcome, get your bicycle headed. Now you know that you're going to overcome inertia. What is it that allows you to overcome it? Well, that's also explained by the second law. In that medical terms, the second law says that force is the product of mass and acceleration. To cause an object to accelerate or speed up, the force must be applied. The more force you apply, the quicker you accelerate. And the more mass your bicycle has, and the more mass you have in return, the more force you have to use to accelerate at the same rate. This is why it's very difficult to pedal a 10,000 bicycle. And it has this force, which is applied by your limits which down the times, allows you to overcome and sustain the inertia. But when you're able to down the times, a bigger the force, the more you accelerate. Now, to the final question. When you think about your mind, as it goes forward, according to Newton's 3rd law, for every action taken, some reaction. To understand this, think about what happens without the bouncing ball. As the bouncing ball hits the floor, it causes a downward force in the floor. This is the action. The floor moves, the same force, but in the opposite direction. Upward, calling its box back into it. Together, the floor obeys its random action failures. When it comes to your bicycle, that's a little more complicated. As your bicycle wheels spin clockwise, the parts of each tire to the front push backwards against the earth. The actions. The ground pushes forward with the same force against each of your tires. The low actions. Since you have 2 bicycle tires, each one takes an action twice at the back. And since the
Okay, so let's dig into it, right? Newton's first law is called the law of inertia. Inertia is the tendency of an object to resist change. In other words, objects that are not moving aren't just going to start moving, and objects that are moving should technically continue to move at the same speed in the same direction forever. Inertia is Latin for lazy. This is the law of laziness. So if a book is on the table, it's just going to stay on the table. It's an object at rest. It's not going to just spontaneously fall off the table. If it does, get out of the house. But also the idea of, something that's going through space, like those asteroids or comets that we talked about when we were looking at balance and unbalanced forces. If something is staying in the same speed in the same direction forever, we call that balanced. Technically, it's an object in motion. That's the first law, right? So we live on Earth, and on Earth, we have lots of unbalanced forces that change an object's motion. So gravity, friction, air resistance, other objects. We have a lot of things that will unbalance a lazy object, that will change the motion of an object at rest or an object in motion. So this is where Newton's law comes in. So we can see our little car sadly getting into an accident with a brick wall. This is why seatbelts are important, right? Because inertia says that the driver in the car will continue to move at the same speed in the same direction. Well, the car stops, but the driver was part of the car's motion. So the driver wants to continue moving forward, which is why car accidents can be really bad when we don't wear seatbelts. The law states, so let's talk about the language of the law. The law states that objects at rest stay at rest, objects in motion stay in motion unless acted upon by an unbalanced force. Yes, ma'am, I'm recording a video. We're all good. So objects at rest stay at rest, objects in motion stay in motion unless acted upon by an unbalanced force. That's how the law is stated, how it's said. So when you answer questions in the future about how a certain situation, like this little test tube guy, how does that show Newton's first law or something like that? I want you to use those words. Well, the object was in motion. And then an unbalanced force of, I believe that's a rock, exerted force on the skateboard, but the test tube man wants to continue moving in the same speed, in the same direction. So he was an object in motion and an unbalanced force acted upon him. So we have some examples of Newton's first law. So we can just look at things that are at rest, like an object on a table. We know that gravity is pulling the object down and that the normal force, which we talked about, is exerting back up on it. We'll come back to that idea of force pairs in the third law. Here we have an object that is in motion, a soccer ball going through the air. Well, air resistance is going to slow it down. Gravity is going to pull it down. The ground is going to slow it down as it starts to roll on the ground. There's lots of things that will be unbalanced forces on this object.
The first part of Newton's law of inertia is pretty straightforward. An object at rest will stay at rest unless and until it causes an unbalanced force. That is, the space mark isn't anywhere. Unless it interferes with another force. Say that this delayed moves so you can say like this. Say the ball stays at rest until someone or something moves it or hits it. The second part, an object in motion will stay in motion until it comes into contact with an unbalanced force. Let me take a bit more information. There are many unbalanced forces in this one. Friction, gravity, air currents, but this example, with this friction, this is so if I have ground, the friction of the belt is going to stop motion pretty quickly. Okay, let's say we're playing this ball. Ice is a smooth surface and a slippery glass in dirt, so it has a lot of friction, but it's still a solid. And it's friction, so the roll is forward before it stops.
Okay, so we have these three images, right? And these should be in your notes as well. So the first one is Stonehenge. Stonehenge is this sort of like unexplained phenomena, I guess, where there are these rock sculptures, and it's in England, Stonehenge, England, and nobody knows 100% how they got there, yet they're still standing. So how is this Newton's first law? Well, the objects are at rest, and they will remain at rest. In lots of movies, they like to show like people backing up into them and tumbling them over, like to be funny. That has not happened in real life, but they would be objects at rest, and they will remain at rest unless acted upon by an unbalanced force. Second picture, you have a golf ball in motion going into its little golf ball home in the hole in the ground, right? So the golf ball is an object in motion, and it will remain in motion until an unbalanced force changes its motion, which is about to happen when gravity pulls it down and it hits the earth, and it stops moving. The third one is a satellite in orbit. So a satellite is in motion. It is locked to the Earth's orbit and moves as the Earth rotates, so does it. So it does move. It's an object in motion. It's probably moving at a constant speed because of that gravitational lock, but it will remain in motion until an unbalanced force either sets it out of its orbit, changing its speed or direction. Newton's second law is my favorite because it's the one we're going to have to know the most about. So Newton's second law says that relationships exist between force, mass, and acceleration. So in other words, it's really a formula. It's a formula of how one of those variables affects the others. So the two independent variables would be force and mass, because we can adjust our amount of force and we can have different masses of objects. The dependent variable, the thing that will be the resultant factor of one of those, is the acceleration of the object. If we use more force, it affects the acceleration. If the object has more or less mass, it affects the acceleration. So in this picture, we can see that this little interesting device of a foot kicking objects has different acceleration. It has the same force because it's set up that way, right? You pick it up, it's kind of a set amount of force. It's very much controlled, but the different objects have different masses, and we can see how the acceleration is dependent upon the mass. More mass, less acceleration, less mass, greater acceleration. And that's the formula. So the formula states force is equal to mass times acceleration, F equals ma. And we have our triangle here, same as we did for distance, right? For speed, distance over time. If I put my finger over the F, then I'm left with the formula to calculate mass times acceleration. If I need to calculate acceleration, then it's force divided by mass. If I need to calculate for mass, then it's force divided by acceleration. It kind of helps you maneuver which variable you're solving for. Here, I can kind of see this at play. I like the second law because it's very visual, because I can tell that in that first picture, it's the same soccer ball. So if I use a small amount of force versus a large amount of force, it affects my acceleration. It's like kicking a ball a little bit or really hard. It's going to send it flying differently. But what if I use the same amount of force or different force on different size objects? I should still see different acceleration.
First law asks what happens when there is no force acting on an object, and the answer is inertia. Newton's second law asks what happens when there is a net force acting on an object, and the answer is acceleration. To be more exact, the law says that acceleration is equal to the net force someone puts on an object divided by the mass of that object. So here's an object. And if someone given a constant force, even though this is a base value, we're going to put an M for mass, because mass is a huge part of the system. We're going to call the net force pitcher puts on F. And then the force the pitcher's hand, it moves with A for acceleration. I'm giving the pitcher the ball, which again is the mass. He's working up some force to put in the mass. Nice pitch, dude. Alright, let's get the bowling ball out here. So let's say you put the same amount of force on the bowling ball. What's going to happen? Now, you're going to put the same force on the bowling ball as you did on the baseball. So that's going to affect the acceleration, right? Let that force work. Same as before. bowling ball didn't go as far. Its acceleration dropped, even though the same force was applied. Same force, but 50 times less. The acceleration drops. Let's write it out. That awesome acceleration you achieved with the baseball, you got that acceleration by throwing the baseball with your net force. If that's a math equation, you're actually dividing the net force you throw the ball by the mass of the ball itself. And that not so awesome acceleration you got with the bowling ball, you got that by applying the same net force to the baseball mass of the ball, which is a mass that is 50 times greater than the mass of the baseball. So you can take the 15 out of this side, that's fine. Yet the acceleration from the bowling ball pitch is 1/50 the acceleration of the baseball pitch. Much slower. That's Newton's second law in action. Acceleration equals net force divided by mass. Newton's first law is
Okay, so let's apply that. We have two scenarios here. The first one says a spring scale is used to apply 4 newtons of force to a toy car with a mass of 0.3 kilograms. What is the acceleration of the toy car to the nearest tenth of meters per second squared, right? So what do we know? We know the force and we know the mass. So we can kind of like keep that in our head. We're solving for acceleration. So if I were to use my formula triangle and put my finger over A, it would leave me with A is equal to force divided by mass. So I substitute what I know, my 4 newtons divided by my 0.3 kilograms, and that should give me 13.3 meters per second squared. Units are important. They all have different units. Force is newtons, mass is kilograms, and acceleration is always meters per second squared. Got to make sure we use our units. Second one, a bowler uses 10.5 newtons of force to roll a bowling ball, and the ball accelerates down the bowling lane at a rate of 2.5 meters per second squared. What is the mass of the bowling ball? So again, what do we know? We know the force is 10.5 newtons. We know the acceleration is 2.5 meters per second squared. So again, if I look at my triangle and I put my finger over M for mass, what I should be left with is mass is going to be equal to force divided by acceleration. I substitute what I know, and I should come up with 4.2 kilograms. Again, you can always pause at any point in the video and then kind of move on from there. All right. Last law, guys, Newton's law of action reaction. A great law, but a little difficult to understand. So I'm gonna do my best, all right? So the first thing we have to know is that all forces act in pairs. And we do understand that because let's go back to the book on the table. We learned that gravity's pulling it down. That's an arrow, right? And the normal force is responding back to keep the book on the table. We have equal and opposite equal and opposite forces. Think about every net force diagram you saw. There was always an object and an arrow going this way and an arrow going this way. If there was an arrow coming from the bottom, there was an arrow going to the top. They always act in pairs. Those forces are equal in magnitude, but opposite in direction. So acceleration will not always be equal because objects aren't always the same sizes. So let's think about that. In this picture, you see the Newton's cradle, right? You pick up one of the little spheres, you drop it, and the sphere at the other end comes up. If I pick up 2, then 2 of them will. It's always equal and opposite, right? That's because they all have the same mass. So the law states, for every action, there is an equal and opposite reaction. So I have 2 examples here. Let's look at bumper cars. We don't know the masses of the kids driving them, but we know the cars are probably exactly the same. So because of that, when they hit each other, that moment that they touch, that's it. That's the third law. It's a law of 1 split second. It's the split second that those 2 cars hit, and we see it. They're coming this way, and then they both move this way, equal and opposite, right? That's the third law. Now let's pretend one of those cars was much bigger than the other. That moment that they hit doesn't change. That they touch each other, it's still like a high five. It's still the third law. But how far they accelerate may change because the objects are bigger. So let's look at the other picture, the hammer and the nail. We know the hammer is much bigger than the nail. That's why it drives the nail into the wall. But that's not what the law is. The law is when they first touch, that first impact, that moment where they first connect to each other or touch each other. That's the third law. It's that tiny little moment that exists right here. That's it. So in the other picture, it would exist right there. That's it. Now, the fact that they're not the same sizes, well, that's another law. That's the second law. Now we're talking about force is equal to mass times acceleration. So this one's a little bit like you have to think of it in just these little split-second moments, okay? So here, Newton's law of action reaction, the balloon goes up, that's a reaction force. The action is the air is going out, which forces the balloon to go up. Action, reaction. The second one is a person pushing on a wall, and the wall pushes back. It has to. So that's that moment where you're pushing on a wall, that contact, just right there, that moment, it's equal but opposite. The fact that the wall has so much mass, though, is what's inhibiting, what's stopping the wall from moving, because we can never have enough force to accelerate that wall. But that's the second law. The third law is just that moment where they touch. That's it.
Hey, man.
You two just acted out Newton's third law. My work here is done. Yeah, you two exerted equal forces on each other, even though one was technically weak. And then you two were ready to do situations. See what I mean? Maybe not. Okay, let's play. So what happened there? You had a beautiful fastball. Actually, the bat hit the ball. And the ball hit the bat. They hit each other equal opposite force. Take a break. See, the ball is object one, and the bat is object two. Object one pushes here against object two. So the bat remains the weight. And object two pushes against object one. So the bat is the weight.
Alrighty, let's finish this up. So the third law, let's apply it so we can better understand it. What forces are acting on a book sitting on a table? Well, there's the downward force of gravity, and then there's the upward force of the table because it has mass and it's pushing back on the book. That's called the normal force, right? So the action force is the book's mass being pulled down by gravity, and the reaction force is the table's normal force pushing back. So they're equal and they're opposite. And that's an easier one to understand because the object doesn't move. It makes sense that they're balanced, they're equal and they're opposite, right? But what if two people are standing on a skateboard and they push off each other? What happens? Well, the action force are the people's hands, just that moment that they connect. So two people on a skateboard facing each other, right? They're like this. Then they reach out and they push off each other with their hands. So that moment that they touch is where the third law comes in. So the action forces are the people's hands exerting force on each other. The reaction force is the skater moving away in an equal and opposite direction. And then it says, well, what would happen if one of those people had a lot more mass than the other? So let's visualize this, right? So second question is that first diagram. They hit each other, and then the bottom diagram, they go back in equal and opposite ways. Makes sense. It seems like the third law. But what if those people were like a giant compared to the other? Well, then they're not going to respond the same because their masses are different. The third law still applies because they're still pushing off each other. It's still going to send them in opposite directions. It's just one's going to go much farther and the other one's not going to go as far because their mass makes a difference. Okay. So there are videos here if you want to rewatch. There's a whole series here about the Newton's laws in space. So all of the laws in space, and then in sports. So we've got speed skating, you've got football, you've got different videos that help you visualize these laws better. And then of course you have an exit ticket, and you will see that this link will be put in the chat, and that's how we'll end class today. Alrighty, bye-bye.